Hi everybody, today we're going to look at 3.9, which is finding the derivatives of general exponential and logarithmic functions. So in order to do this, I want to review expanding logarithms first as our warm-up. So remember, anytime when you have operations inside of a logarithm, whether it's multiplication, division, or exponents, we can expand and break this up into multiple logarithms. Multiplication gets broken up into addition, and division gets broken up or expanded into subtraction. And then finally, the exponents come down as coefficients. So ln 3 plus 8 ln y minus 4 ln x. Okay. And the second one, the addition and the subtraction inside of those parentheses cannot be broken up, but the individual factors can. So ln of quantity 2x minus 1 plus ln of quantity x squared plus 7 minus 1/2 ln quantity 3x minus 5. Okay. So for our first rule here, deriving b to the x. Well, I'm going to rewrite this and prove this, but we have already learned that the derivative of e to the x remains e to the x. Okay? So I can actually rewrite this as the derivative of e to the ln b of x. Okay? Remembering that e to the ln are inverse operations and they would cancel out and bring us back to the b to the x. So if I do it in this way, then I can think of it as the chain rule. And therefore, right, my inside is the ln bx and my outside is the e. So outer prime remains e to the x, or e to the ln bx in this case. And my inner prime, the derivative of ln bx, it's really just ln b times x is what's happening here. It's really just a coefficient. Ln b is an irrational number. X is a linear term. So the x would disappear and we would just have this ln b. And then I can simplify my final answer, remembering that e to the ln of b would cancel out inverse operations. So I am left with b to the x power times ln b. So the only thing that's different between deriving an e to the x and deriving a b to the x is we have this additional ln b. We don't need it for our e to the x because ln of e is just equal to 1. So that's why we were shown this rule of e to the x derivative of it early on, because it simply remains exactly the same. With the b to the x, we have to remember to attach through multiplication ln b. So you don't have to prove it ever again. I just wanted to show you that this rule exists. Now we can just apply it. So the derivative of b to the x equals ln b times b to the x for all b's greater than 0. So if we wanted to derive 10 to the x right away, our answer would just become ln 10 times 10 to the x. And if we wanted to derive 6 to the x, we would have ln 6 times 6 to the x. Now, as we continue to move through this chapter, I'm always going to introduce these rules as they are, but also in conjunction with a chain rule. So if we were to think of this as a b to the u instead of just a b to the x, u implying that the exponent, the input, is something other than x. So then I would be deriving this with a chain rule. The outer is the b to some power, the inner is the u. So the rule for the b to the u would be ln b times b to the u, and then for chain rule we would multiply by u prime. So it might help to remember these rules as a chain rule instead of just the rule in isolation. So now for these next examples, if we wanted to derive 4 to the 3x, here's our b to the u rule. So b to the u becomes ln b times b to the u times u prime. So f prime of x is going to equal ln of 4 times 4 to the 3x times 3, where the ln b times the b to the u portion is the rule for the b to the x prime, and the u prime comes because it's a chain rule. The only way I would really clean up my answer for this one, I would put the 3 out in front. 3 ln 4 times 4 to the 3x. Okay, so the second one, same idea. F prime of x, right? ln 5 times 5 to the x squared times 2x. Okay, go ahead and give these 3 a try. So pause the video, fill them in on your own, and then check back in once you've finished. Okay, so the first 2 are very straightforward. The third one's not so bad. It depends on how you approach it. But I'll tell you that one of the keys to fully understanding and getting these types of questions correct on the AP is being able to manipulate and use your properties of logarithms. So in ln root 2, that's not an incorrect answer, but remember that that's equivalent to 1/2 ln 2. Likewise, root 2 to the x is not wrong, but you could rewrite it as 2 to the x over 2 power, or 1/2 x power. Okay. So now, we're going to move into deriving ln x, or logarithms. So first of all, I want you to let f equal e to the x and g equal ln of x. And remember that these are inverse functions. Okay. We know the derivative of f prime is e to the x. And if we know that we have inverse functions, we can find the derivative of g of ln x using g prime x equals 1 over f prime g of x. So I'm just going to prove this, and then once we have it proven, we've established a rule. So using this, g prime of x is then going to equal 1 over f prime of g of x. So f prime is e to the x, so we would have e to the ln x. E to the ln cancels out, and we just have x, which means that this simplifies to 1 over x. Okay? So the derivative of ln x is always going to derive to 1 over x. Again, I want to show it to you in conjunction with chain rule. So if we have ln u, where something other than just x is in there, it will derive to 1 over u times u prime, or u prime over u. Get familiar with that one, because this one will come up a lot, u prime over u. Okay, so there's your rule. Now let's take a look at this rule in conjunction with a product and then a chain. So ln u, I like to use this arrow. It's not proper notation, but when I write the arrow, that implies that I'm showing you what the derivative is. So if we have y is equal to x times ln x, right? Remember to kind of say out loud where that multiplication is. Now I consciously see that I have the product rule, which means I have f prime g plus fg prime. Right, so y prime is going to equal, I'm just going to set it up this time, x prime ln x plus x ln x prime. Go through and derive it. X derives to 1, ln x stays, ln x derives to 1 over x. So final answer, ln x plus 1. Our second one is a chain rule, where the outside function is quantity squared, the inside function is ln x. So chain rule says derive your outer, keep the inner the same, so 2 times ln x to the first power, and multiply by the inside prime. Derivative of ln x is 1 over x. So you can write your final answer here is 2 ln x divided by x. Okay, here's another chain rule, but now the outside function is the ln, the inside function is the x cubed plus 1. So this is a u prime over u problem. I'll set it up the long way, and then when you're comfortable, you can kind of condense it to the u prime over u shortcut. So my out, right, is ln something. My in is x cubed plus 1. My out prime, ln something, would go to 1 over that something. My in prime is 3x squared. So if I put my chain rule together, out prime with in original, 1 over x cubed plus 1, times in prime. Then I can put that together as a single fraction. And hopefully you're seeing that the top is my inside prime, the bottom is my original inside. The ln is gone by the nature of its derivative. Here is a double chain rule. I have an ln, then I have a square root, then I have a sine. So I have basically 3 functions composed together, right? An f, a g, and an h. You don't have to think of it that way. When you're doing multiple chain rules, think of it as deriving 1 layer at a time, outside in. 1. Okay, so the first thing that I want to derive is my ln. ln says 1 over inside. The next layer is the square root. The square root derives to 1/2 inside to the negative 1/2. And the final layer is the sine x going to cosine x. Right, 1 layer at a time until I finally got to the innermost function. I can simplify this together. I have a cosine x up top. I have a 2 on the bottom. And I actually have square root sine x times square root sine x on the bottom, which would just be sine x. And then if I have a cos over a sine, I have a cotan. So I really have 1/2 cotan x. They don't always simplify this nicely, but if you can, I would like to see the final answer like that. Okay, so 3 more for you to try on your own. The parentheses should show this on number 3. Give it a try, and I'm going to leave these blank. I'm going to have us do these in class together. Okay, next concept here. So we've talked about how to derive an ln, but what about if we have a log of a different base? So we need to use that change of base formula for this rule. Anytime you have a log of a different base, it really can be rewritten using ln x over ln b. And what I want you to acknowledge is that the ln b portion, 1 over ln b technically, is a number. It's a coefficient. It's irrational, but it's still just a coefficient. Okay, so therefore it doesn't really impact the derivative. It's not creating a quotient rule. So if we want to derive log base 10 of x, the first thing that we want to acknowledge is that we are deriving ln x over ln 10. I would like to see you consciously think about this through separation, that it's 1 over ln 10 times ln x. And I'm saying this because I'm hoping that you acknowledge that the 1 over ln 10 doesn't get derived. It's just a constant out in front. So 1 over ln 10 stays, ln x derives to 1 over x, and that would be your final answer. Okay, so anytime you're deriving a log that is a different base, you are then going to kind of pull out the base as the coefficient. So for example here, f prime of w is 1 over ln 2 times 1 over w. The second one, which is a little bit more complicated, we first would write it as ln of 2z squared plus 7 divided by ln 5. So when I derive this, the 1 over ln 5 pulls out, and then I have a u prime over u. So the inside is 4z, inside prime, and the original inside stays in the denominator. So final topic of this section, it pulls together some of these ideas, but it is a little bit long. So it's called logarithmic differentiation. There's going to be times when we use this out of preference, and then there's going to be times that we use this out of necessity. So in class we'll go through some examples together, but it can be very, very helpful. The way I look at logarithmic differentiation is it is a way to avoid multiple chains or multiple quotient and products, all of these rules together. And that way we can use this process and repeatedly use u primes over u's to get through it. So the definition up top, if we're deriving ln of f of x, that's the rule that I've already been telling you all this whole section. It's the same as saying u prime over u. It's my notation for that. So these are the steps for logarithmic differentiation. If you approach a problem that is long, difficult looking, or there will be times when you can't get to the actual function that you need to derive and you need to apply an ln, using ln allows us to expand using properties of logs. Once we're fully expanded, we can differentiate, and finally we would solve for f of x. Sorry, that's a typo. You should be solving for f prime of x, not f of x. Okay. All right, so here's the first example, right? It has multiple chains, it has product, it has quotient. So this is a problem that we could apply logarithmic differentiation to. So if I apply an ln to both sides, remembering that the left-hand side is just as important as the right-hand side. It's ln of f of x. The right-hand side, this is why I had you warm up the way you did with the do now, we now expand, right? Multiplication goes to addition, exponents go to coefficients, and division goes to subtraction. So we have 2 ln of x plus 1 plus ln of 2x squared minus 3 minus 1/2 ln of x squared plus 1. So what I've just done is I've removed all of the extra rules. I've taken out the products, I've taken out the quotient, I've taken out the additional chain rules, and the only rule that I'm going to be using through the derivative process now is my u prime over u. So now I can derive everywhere, left and right. So if I derive the ln of f of x, I get f prime of x over f of x. That's the same thing as the u prime over u. When I derive each individual term on the right, the coefficients would stay, and I would have u prime over u. So x plus 1 prime is 1 over x plus 1, plus u prime over u again. 2x squared minus 3 prime is 4x over 2x squared minus 3, minus 1/2 stays. X squared plus 1 prime is 2x over x squared plus 1. My final step is to solve for f prime, so I need to multiply to the other side. And f is the original function that was given. You don't have to simplify this. You definitely don't need to distribute terms. You just need to isolate f prime. So f prime is equal to 2 over x plus 1 plus 4x over 2x squared minus 3 minus a half times 2x over x squared plus 1. All times x plus 1 quantity squared, 2x squared minus 3 over square root x squared plus 1. And that's the process. So I do have a few more examples left in these notes. I'm going to leave them blank and we're going to do them together in class. Okay, so that's it for 3.9.